Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at rates of change. Now, we've actually looked at rates of change quite extensively for linear functions because the rate of change of a linear function is very easy to understand. The rate of change is just the gradient. What makes linear functions so easy to work with is that their gradient or rate of change is constant. It doesn't matter where you pick the points. I can pick these 2 points here. The gradient between them for y equals 2x is equal to 2. That would be the same answer I get as if I pick these 2 points here. I would also get a gradient of 2. The gradient is the same everywhere along this line. That's why it doesn't matter where you pick the 2 points for a straight line, you will always get the same gradient. But what about for a nonlinear function like y equals x squared? This isn't exactly a complicated function, but what if we were to look at the gradient of this curve in red? Well, let's look over here at this region. So as we're going to the right, the x values are increasing, but the y values are decreasing. That means that the gradient of this curve would be negative in this region. Around here, it's very flat, it's almost horizontal. So here, the gradient will be close to or equal to 0. And of course, over here in this region, as we're going across to the right, x is increasing, y is also increasing, so the gradient would be positive. That's what makes this curve challenging to work with. You would get a different gradient for different regions of the graph. And it turns out the gradient of this function is actually different at every single point. That's what makes this challenging. So what if I wanted to find the gradient of this function at the point, say, where x equals 2? I want to find the gradient there. It's not easy to do because I can't just pick any 2 points because the gradient is different depending on the points you pick. So let's illustrate that. Let's calculate the average rate of change of the function between this point, x is minus 3, and x equals 2. What I can do is I can calculate the average rate of change that's occurred from here to here simply by finding the gradient of this line. So this line hits the curve twice. It is called a secant. Now, finding the gradient of this line in green is actually really simple. The gradient is simply y2 minus y1 over x2 minus x1. So it's negative 5 over 5, which is negative 1. That's the gradient of this line here in green. So that tells us the average rate of change between these 2 points. But you can see clearly that this line is not a good indicator of the rate of change of the function at this point. This line in green isn't going in the same direction. The curve is going in that direction, so it has a positive gradient. But this line here is going in the complete opposite direction, which is why it has a negative gradient. So this line here is just the average rate of change of the function between those 2 points, but it doesn't tell us what the gradient is at this particular point. It does a very poor job. So how about if I want to estimate the rate of change at this point, instead of picking the point over here, I'll pick a different point. I'll pick this one here. So I'm going to draw another secant that goes through the point where x equals 0 and where x equals 2. So that line in yellow is another secant. So to calculate the gradient of that line, all I do is use gradient equals y2 minus y1 over x2 minus x1, and I get 2. So that's the average rate of change of the curve y equals x squared between x equals 0 and x equals 2. It's just an average rate of change. It's still not a great indicator of the gradient of the red curve at this particular point. You can see that the line's going in this direction, the curve's going in this direction. So they're still going in different directions. Okay, what about if I choose this point instead of this point? So once again, I'm going to draw a secant through those 2 points. So This line here in pink is another secant. So the gradient here is simply y value of the second point minus y value of the first point over x value of the second point minus x value of the first point. So I get here a gradient of 3. Now this line here in pink still isn't perfect. It still isn't fantastic at indicating what's happening to the red curve at this point. It's not quite going in the same direction, but you might see a pattern here. The pink line is much closer to the curve around this point than is the yellow line. And the yellow line is much, much closer to the red curve at this point than is the green line. The closer together the 2 points are, the better the secant represents or follows the curve at the point in which we're interested. So each of these 3 didn't give me the exact gradient of the red curve at the point where x equals 2, because they're just average rates of change. If I really want to estimate the gradient of this red curve at the point x equals 2, I need to pick 2 points that are very, very close together. So if I pick 2 points that are close together, I'm getting closer and closer to calculating not the average rate of change, but the instantaneous rate of change. Remember, I said that at the start, the gradient of the red curve is different at every single point. So my goal was to calculate what the gradient is at just this point here. It's kind of like at an instant, which is why we call the instantaneous rate of change. Now, as I've seen, calculating the average rate of change isn't entirely accurate, but it will be more accurate if the points are close together. So if I want to just estimate the gradient of the red curve at this point, I need to pick 2 points that are very close together and calculate the gradient of the line that goes through those 2 points. So to do that, the gradient will be y2 minus y1. Now, if x is 1.99, the y value is just 1.99 squared. And that gives us 3.9601. On the bottom, it's x2 minus x1. So you can put this straight into your calculator and you get 3.99. So that is our best estimate for the instantaneous rate of change, for the gradient of the red function at this point. Now, it turns out that the instantaneous rate of change is exactly 4. To calculate it exactly requires calculus that's beyond the scope of this course, but you will learn one day. We do that through a process called differentiation. But for our purposes now, if we want to estimate the instantaneous rate of change, we want to calculate how quickly a function is changing at a particular point. In other words, the gradient of a function at a particular point, we just pick another point that is very, very close to that point, and we find the average rate of change. The closer and closer together the 2 points are, the better the line between them will mimic the curve at a given point. If the points are getting closer and closer together, this secant is getting closer and closer to a tangent. Because of these points where x is 1.99, which is about there, if we draw a line between those 2 points, it's starting to look more and more like a tangent, like a line that only hits the curve once. So tangents are lines that hit the curve once, secants hit the line twice. So the instantaneous rate of change is basically the gradient of a line that is a tangent to the curve at that point. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.